In this video, we will define what a function and what a relation is, as well as what a domain, codomain, and range is. And we will use these definitions to, in the next video, define what an injection, surjection, and bijection is. And those are all types of functions that we concern ourselves with in discrete math. But for now, let's define what a relation, what a function is. So a relation with domain A and codomain B is any subset of the Cartesian or cross product of A and B, right? So for the sake of an example, let's let A be the set 1, 2, and 3, B be the set 4, 5, and 6. And as an example, we can let some relation R on this domain and codomain be, I don't know, let's say 1, 4, 2, 5, 2, 6. Okay? So this is an example relation with this domain and codomain. A function is also a relation, right? So it's also a subset of the Cartesian product of domain A and codomain B, but it satisfies the property that for every element in the domain, there's exactly one corresponding element in the codomain, right? So another way of saying this is for every element in the input, there's exactly one output, okay? So not multiple outputs, not zero outputs. There's exactly one output for every element in the input. Cool. So the first question is this above relation R a function? Because all functions are relations. So functions are subsets of relations. But not all relations are functions, right? Because a relation could not, in theory, satisfy the property that there's exactly one element in the codomain for everything in the domain. But all functions are subsets of the Cartesian product of domain and codomain, so all functions are relations. It turns out that R is not a function. And it's for two reasons. Well, one, it's that the input of 2 has multiple outputs. And that's not allowed in terms of the definition of a function, right? As well, there's no output for the input 3. And for a relation to be a function, there needs to be exactly one output for every input. So input 3 has no output. So that's why R is not a function. An example function with this domain and codomain could be, let's say, 1, 5, 2, 5, 3, 6. For now, it's okay that we've repeated the output 5 and 5, right? Functions only care about there being exactly one output for every input. It doesn't matter if the outputs are repeated. Cool, so that's a function. One thing to note is that domains and codomains don't necessarily have to be numbers, right? We could have functions of vectors, functions of matrices, and in this case, we could have functions of letters, right? Because for now, all we've seen is that functions are sets, nothing but sets of ordered pairs. Okay, so in this example, we have A being the set of the words hi and hey, and B being the set of numbers 5 and 10. And so A cross B represents all possible combinations of one element in A and one element in B, and our job is to figure out whether or not F, G, and H are functions. They're all relations on A and B, but our job is figuring out whether or not they're functions. So let's check F first. Does it have an output for the input hi? Yeah, it does. Does it have multiple? No. Does it have an output for the input hey? Yep, and it has exactly one, so that means F is a function. G, does it have exactly one output for the input of hi? Yep. Does it have exactly one output for the input of hey? Yep, so that means G is also a function. Now let's look at H. Does it have exactly one output for the input hi? No, it has 2 of them. Additionally, it has no outputs for the input of hey. So there's 2 reasons why H is not a function. No output for hey. We have 2 outputs for hi. So H is not a function, whereas F and G are indeed functions. Now let's talk about what the definition of a range is. So as we know, a domain is all possible inputs, and the codomain is a set of all possible outputs. And to write that symbolically, we can say f is a function that maps elements in the input or the domain to elements in the codomain. We can also write it like this. F takes elements in A, sends them to elements in B, okay, with this arrow. A range, instead, now, is the set of all actual outputs of a function. So the domain is a set of all possible, range is a set of all actual outputs, okay? So in some functions, the domain and range are equal, in that all possible outputs are all actual outputs. So every possible output actually occurs as an output. But this is certainly not true of all functions. Okay, so for f and g, remember the codomain is the set 5 and 10, because that's the set of all possible outputs. Now our job is to figure out whether f and g have the property that the codomain and range are equal. Okay, well, what are all possible outputs in f? What are all actual outputs in f? The possible ones are 5 and 10. What are the actual outputs in f? Well, it's 5 and 10. So f has the property that the domain and codomain are equal. In G, what are all actual outputs? Well, they're both 5. So all actual outputs in G are 5. So for G, it is not the case that the range and codomain are equal. G is still a function, but the codomain is not equal to the range for G. Cool. And this is a nice little diagram taken from Wikipedia that sort of explains the relationship between domain, codomain, and range. So this red region here is the domain, it's the set of all inputs. This yellow region is the range, it's the set of all actual outputs. And Y is the codomain, the set of possible outputs. And again, we're using this notation, F maps elements from X to elements in Y. Cool. The last thing we need to talk about before getting into the different types of functions we study is how we can represent functions. So far in this video, we've represented functions as sets of ordered pairs, as something like 1, 4, 2, 5, 2, 6. And that's that's not a function, but let's say it's 3, 6. Okay? And that's a perfectly valid way of defining functions. However, in most cases, we'll be dealing with infinitely large input sets and output sets. So if, for example, the function f of x is equal to x squared, there's no way you could list out all ordered pairs in that, right? So what we usually do is specify some rule that describes how to get from input to output, right? And this rule, even though most of the time it doesn't necessarily have to be algebraic, right? So for example, f of x maps numbers x to the x smallest prime number. That is a perfectly valid function, okay? But the functions you will usually see will look something like f takes in some number x and spits out x squared. So this is an element domain. X is in the domain and x squared is in the codomain. Okay, another way of writing f of x is equal to x squared is f maps elements x to their outputs x squared. And so notice this flat tail. It means maps to. So this arrow with the flat tail means maps to, okay? Whereas on the previous slide, when we use this notation A maps to B, we didn't use the flat tail. So here we're talking about the sets themselves, and here we're talking about the elements. Okay, so that's a little bit of notation for you. So now we've defined all the properties of functions that we care about so far. Now in the next video, we'll go ahead and talk about the kinds of functions that we study in discrete mathematics.